So maybe I just say a few words before I get to content of what my hopes are for this live stream and the kind of audience I have in mind and the sort of the format of this whole thing. So for quite some time now I haven't posted any serious new YouTube videos, and I was always a bit hemming and hawing and because producing videos takes a long time. And I think live streaming now is a good option to just upload out content and there's no editing, it just has to go out. Because I have a lot of ideas that I try in class and talk about with other people, but never really in that much detail. So this live stream will mainly be geared towards teachers. But I think it will be focused enough on content that people who are just interested in that because they're self-studying, for example, can take some things with it. But I would intersperse the presentation with some ideas on how to convey this as a teacher to students. But it will be content-focused. Because this is something that I really see in mathematics teaching that is lacking, that we are not critical enough of the content itself. We sort of have this idea that, well, the way we solve things, the formulas we have, the theorems we have, and the proofs that we give are, well, done, and now we just have to think about how to convey that to students. But I think if we really reflect on content itself, we can simplify a lot of things and find simpler and more intuitive approaches to formulas. So you can post questions in the chat, and I will just see myself how much I can answer them or get to them. And so I really don't want to go into these kind of questions about IQ. Not that I don't have lots of thoughts about it, but it's not on topic for today. And after all, there's a lot more to the worth of human being than a single number. Okay, so the original reason for... Okay, hang on. Yeah, I can fix the echo. I think this is it. Can you tell me if there's still an echo? So a few days back, Eddie Wu shared some content on Twitter about how he teaches, or how he tries to convey intuition for the dot product in geometry. And it wasn't really a worked out proof or derivation of the formula, but it just wanted to convey the sort of what's it called, a mnemonic for what does it mean for the dot product to be positive and negative. So whether we go the two vectors are aligned, go in the same direction, or they go in opposite direction, or they're perpendicular. And this has sparked some thought in me because a few years back I posted a video on how to teach the dot product, or how to show why the two formulas for the dot product coincide. Oh, hang on. I'm sorry about that. Yeah, I don't know. It's usually I have all my things on Do Not Disturb, but I don't know what happened. Okay, so but I wasn't really happy with the video. Maybe some of you have seen it, so when working on a new approach, and also a new approach on the cross product. So the question is, how can the formulas for the dot product and also the cross product arise naturally as questions to natural answers? Usually, I mean, the formula for the cross product is quite involved, and I was never really happy with it. So the plan is, I first want to talk about the dot product and some new, an approach that I would find quite nice, that sort of makes the formula pop out quite naturally out of very simple considerations. And then I want to go to the cross product and talk about that, and even have that formula pop out quite naturally. So for me, the starting point is, and for that I now switch to here. So the starting point is, I imagine a class that is familiar with vectors in the sense of displacements. So when I draw something like this, here's a vector v, and then we say it has components 3, 2, that this is what people are familiar with, right? And then we can say, for example, scale a vector or add two vectors. So maybe this is a vector w, and that is 1 and negative 3, and then we can add. So this is the kind of level that I'm aiming at. And now one question is, when we look at the components, how can we check whether two vectors are perpendicular? So this is what the dot product asks. So right, when are v and w perpendicular? And that means from the components. So I give you 4 numbers, and it's your job to do some computation with it and tell me whether these vectors are perpendicular or not, right? And at first glance, this is quite if you don't know that it has something to do with dot product, if you don't have the concept of a dot product, it's kind of, you don't really know where to start. But there's a very similar question that a lot of students have right off the bat, they write intuition for it. And that's the question is, when are v and w, and I try to make an effort to do better writing, parallel? So I give you 2 vectors, say the vector 2, 1 and the vector 6, 3. Actually, let's make it more interesting. Let's make it the vector 4, 2. And what do you do in your head when you try to ask if these 2 vectors are parallel? Well, you can of course draw them out. Say, okay, v is, what is it? It's 4 across and 2 up. And w, where are my colors? Okay, yeah. So the other question is, how do we turn a vector by 90 degrees? Because then, right, we can say, for example, v is, let's take the example from before, is 4, 2. And it's actually quite natural if you ask students to draw a vector, turn this by 90 degrees, that they do this. And obviously, this is the vector, let's say, v prime, and it has components negative 2, 4. Yeah? This is how we turn a vector by 90 degrees. And the general rule, if you have a vector v1, v2, and then we flip the components and then change the sign on the first component. So this turns a vector 90 degrees counterclockwise. And now we can say, well, 2 vectors, well, let's call them v and w, are parallel exactly when the turned version of v is parallel to w. Yeah? So that is, this vector is parallel to w. And what is this? Well, we can just cross multiply. That means negative V2W2 has to be the same as V1W1. Or more cleanly, V1W1 plus V2W2 must be 0. So, I hope you recognize this already as the dot product. And you see where it comes from. It comes from this cross multiplying in the proportion. Just to, one of the two is we have this flipping and changing the sign. But it's essentially what we do. This is where this comes from, right? And from here on, you can study the properties that it's you can add two vectors and this that it's distributive. So for example, u plus v dotted with w is u dot v plus u dot w, etc. Yeah, but I really like this approach that you can arrive at the formula not just by defining it and saying, oh, that's what this is. Don't ask where this comes from. Just someone had this idea. Yeah, but it actually comes from a natural investigation on when are vectors parallel with proportionality and when are they perpendicular by turning one of the vectors by 90 degrees. Okay, so the next thing is the other formula for the dot product. Yeah, so we also have this thing where this is sort of the length of u times the length of v times the cosine of the angle between them. And actually, I try to force myself to call vectors v and w, because I don't know about you, but whenever someone calls two vectors u and v written by hand, then you can never really tell them apart, u and v. But where does this come from? And this is something that I've explained in a video a while back. That is, if you think of these two vectors as one being a displacement vector and the other being a gradient of, say, temperature. Yeah. So say, for example, v is a displacement vector. Yeah. And let's actually give it units, 3 centimeters and 4 centimeters. And w is a gradient for temperature, right? And let's say it has components 3 degrees Celsius per centimeter in the horizontal direction and 4 degrees Celsius per centimeter in the vertical direction. Yeah. So this means that we have some surface, or plane, and it has these varying temperatures. You could also think of this as varying heights, so that these are what's it called, like height lines, and they form lines. But you can also think of it as temperature. Yeah. So maybe up here it's very hot, and then it's sort of moderately hot in the middle, and then it gets rather cool over here. And what this W means, that for every centimeter in the x direction, we gain 3 degrees Celsius, and for every centimeter in the y direction, we gain 4 degrees Celsius. This is what a gradient expresses. And then we ask, well, how much does the temperature change along this vector 3, 4? So here this would be 3 in x direction and then 4. I should have planned this out more carefully. In the y direction. Yeah? And we ask, what is the change of temperature along this vector? It's quite natural to look at it separate in x and y separately. to say, well, we move 3 centimeters horizontally, and for each centimeter we gain 3 degrees. So we gain 9 degrees horizontally, and in the y direction it's 4 centimeters and coincidentally also 4 degrees Celsius per centimeter. Yeah. So along V we gain, so it's 3 centimeters times 3 degrees centimeters, so 9 degrees Celsius horizontally, and in the y direction it's the same with force. Yeah. So we gain 25 degrees in total. So we actually essentially computed the dot product of V and W. And we split this up in the x and y direction. But there's another way of looking at it. The other way is to say, well, V goes about from the cold to the hot, so it's not something that goes this way, for example, right? So there should be a direction in which the temperature rises the most. And we can actually think about it if we think the other way around. In which direction does the temperature not change at all? And that is, for example, I hope I get this right, this vector here. Do I have a new color for that? Here. So this vector here, yeah, let's call it u. And u is negative 4 centimeters and plus 3 centimeters. And if we compute u times w, we get negative 4 times 3 plus 3 times 4, so it's actually 0. So there's no change in temperature. So along this line, we always have the same temperature. It's an isotherm. And that means that every parallel to that is also an isotherm. And if we go at right angles, that would be here, this is the direction of steepest temperature increase. Yeah. And well, the V that it shows I think it shows a V that is already perpendicular. It's a bit badly drawn, but I think V was 3, 4. Yeah, and that's perpendicular to negative 4, 3. But say we have some other V. So let's say we have a V being, oh, I don't know, 5, 1. Yeah. Then first let's do the component formula. So it's 5 times 3 plus 1 times 4, that's 19 degrees, right? From here we go 1, 2, 3, that way. But another way of saying how much does the temperature increase along this vector is to say, well, along this direction the temperature increases the most, but perpendicular to that it doesn't change at all. So the only part that interests us, that makes a change, makes a difference, is this vector here. Oh geez, I don't know why, but my drawing skills are abysmal today. So if this is all that interests us, what we actually need is the length of V, how many centimeters do we actually move, and then we project that, and there's the angle theta, onto W, and then we just say, okay, how much length is that times how many degrees per centimeter do we get in that direction, right? So we actually take the length of V, which is, I don't know, square root of 26, I think. Yeah. So we project it onto W, and then we just multiply with the length of W, right? So we actually do this V times the cosine of theta, and then times the length of W. Voila. This is here. If you want to go back and watch the video that I did a couple of years ago, that explains this whole point a bit more visually appealing. So this is how I sort of justify that these two things are the same. These two formulas both work. So I wasn't really happy with this approach because it treats V and W in different ways. One is the displacement vector and the other is a gradient. Already a gradient is quite a high concept, and it sort of mirrors what later on in college you call covariant and contravariant vectors, and then you model them as row vectors and column vectors. And that's a level of sophistication that I really did not want to have in this exposition. Because also, it really starts with the symmetry. V times W is the same as W times V. Yeah, computationally, yes. Yes, of course. You see it in this formula. And we see it in this formula. But both formulas essentially treat V and W as different things. They have different units even. So where's the symmetry? Yeah. So this symmetry is broken. Yeah. It's sort of formally there, but it doesn't work with the units. Yeah. So there's no symmetry in the units. So I was looking for a way to show the dot product in a way where we can just take two displacement vectors, right? And this is what this approach led to. But there's another open question here, which is, well, if you think of these as two displacement vectors, this is a length times another length, that's an area. And then we add another area. Where's that area? Yeah. Where is the area? Right? If we treat the two vectors separately as a displacement vector and a gradient, then the dot product is just a temperature. Yeah? But if both are length vectors, which is the most intuitive or straightforward way of thinking of a vector, it should be an area. Where's the area? It took me a while to find the area, but it's there. But I can get back to that later. So actually, my original plan was to make this about an hour, but since we've lost so much time at the beginning, I would say an hour from now. That's sort of my goal when I want to be finished. So we have this open question where the area is, and I have to put this aside for a while. And next step is, how do things look in 3D? Because in 3 dimensions, we say V times W is V1 W1 plus V2 W2, and then we just assume that no one would complain or ask any questions if we just add this third term to the formula. But it's not that obvious, right? And one way to justify this is to go with a line and a plane equations. So with a line equation in 2D, it's this a times x plus b times y equals, let's say 0. Let's make a line that goes through the origin. Yeah? And what that means is that the vector xy is perpendicular to the vector AB. So if we draw the vector AB somewhere, we know that the line that is described by this equation consists of all the points whose position vector is perpendicular, right? So it's, which one is it? This? Yeah, this one. Right? And then in 3D, we have plane equations. Then we write ax plus by plus cz equals 0. And in this picture, it's much more natural to accept that it just goes on, the third dimension just is this one more term. But you can also think of it as this. If we solve it for z, it's z is negative a over cx minus b over cy, I think, right? So it's a linear function of x and y. Yeah. So we could say if we sort of vary x and we keep y constant, we move along a line anywhere, and the same way in the other way around. So we have a surface that whichever way we cut it, we always get a line. So this must be a plane. Yeah. So in this like linear equation land, it's quite natural to understand why this must be a plane. Yeah. But you already see from this formula, this just means that x, y, z is perpendicular to some vector a, b, c. Right? So this sort of is maybe not a rigorous proof, but a good motivation of why we can just add this part here. And the last thing, but it's actually something I want to leave out for you to work on, is to fill in the detail, why does the trig formula also work in 3D? Yeah. So that is something that you might want to think about and fill in the details. But I think you should have, everything should be in place now. So this new approach for the dot product is something that I haven't tried it out yet, but I found it really nice that it follows nicely from just proportions. But I don't want to stop here. I want to look at the cross product now. How far can we take this approach of asking natural questions and extending them also to 3 dimensions to get at the formula for the cross product? And as it turns out, you can get the formula for the cross product without too much computational work, and also teaching some deeper principles about mathematics, or in general. You see what I mean. So, but at first, let's go back into 2 dimensions. So, because there's a cross product in 2 dimensions as well, so remember that the cross product in 3 dimensions, it's sort of supposed to be a formula to compute the area of the parallelogram spanned by 2 vectors. Why that would be is really, really not obvious. But we can ask the same question already in 2 dimensions. Yeah. So in 2 dimensions, let's just have you know what? I need to get off this reflex of always drawing coordinate axes. Yeah? Very often, it's really not that necessary to draw axes. Yeah? If we're talking about vectors, I mean, I can just draw a vector here. Here's a vector. Yeah? And here is, let's say, another vector. Yeah? All we actually need is the grid, yeah? the graph paper grid. And then we can ask, well, what is this area? Right? And that's quite a natural question, because we know this from multiplying integer numbers. If the 2 vectors are perpendicular, or one is horizontal and the other is vertical, well, we know what this is. I mean, this is V, this is W, this is V times W. Yeah? And if one of the two vectors is negative, so let's say this is negative V, then we know this from integers that this is actually, let me write it like this, that the product flips signs. So this idea of an oriented area is something that we can already take from just working with integers. Yeah, exactly. We need to multiply just the values of both vectors as they're just perpendicular, but it's nice to keep track of the sign. So this idea, now we want to decouple from the right angle. We're just in 2 dimensions. And to find this area, there are 2 approaches, or 2 ways you can also have students do it. One approach that students can handle quite well is to decompose it into vectors. And I would recommend that you first do it with just numerical values. You give them actual coordinates, and then only in the second step do it algebraically. Yeah? And let's see what this is algebraically. All right, let me draw this again, like this. And then, so I draw a box around it, and then we do a little decomposition. And this is the area that we want to get at. Okay. What are the lengths? This is V1, right? This length here is W1, right? It's the x component of the green vector. And then this is the y component of the green vector, and this is the y component of V. And all these components, I draw them positively, but you need to check that this also works whenever any of these is negative. So the whole area, the total area, is V1 plus W1, V2 plus W2. And then we take off little areas here and there, right? So we take off, this is W1, V2, and then we take off, it's actually the same one, right? And then we have this little triangle here, which is W1 times W2 divided by 2, but we have 2 of them, yeah? And then the same thing with this little one, which is V1, V2 over 2, but we have 2 of these. And if you expand this, you actually arrive at V1, W2 minus V2, W1. So you might already get this feeling of, oh, this actually has something to do with vector product. Yeah. So this is what I wanted to decompose into areas. But the other method is to decompose it into vectors, or decompose it into components. And this is a quite general technique that is really fruitful in analytic geometry, to ask first what is the behavior for unit vectors, and then check how these unit vectors compose into general vectors, right? So we first ask what should, and at this point I think I need a notation for this area. And I want to use this notation here with a little angle bracket. First of all, it's not the cross product. We're not in 3D. But but I also don't want to use the notation for cross product, because I have my reason for that. You will see that later. So we ask, what should the general formula for this kind of new product between two vectors be? And this is the answer that we want to get at, right? Be for the unit vectors first. And our guiding principle is that it's supposed to be this area, right? We need a formula for this area. So if we say, for example, give it E1 and E2, we want this area, right? So we actually want 1, 0 and 0, 1. They should give 1. But the other way around, 0, 1 times 1, 0, well, it's sort of a bit like the sign is flipped, right? Maybe it's not too obvious why, especially to a student, why we would want this to be negative. But you can, for example, ask, what should it be? What should be the product between 1, 0 and 0, negative 1, right? So it's E1, but then negative E2. Yeah. And in one sense, yeah, we want this to be just 1, but in the other sense, you can think of, well, we've had a sign flip here. Yeah. And it's quite natural to think, well, if this thing becomes, for example, 2, we have twice the area. If it becomes 3, we have 3 times the area. Yeah. So maybe you can already write, I want 1, 0 times 0 something, y. I want this to just be y. Or even generally, if there's an x here, I just want it to be x times y. And this forces me to also account for negative signs. To say, well, okay, it's not quite the area, it's the negative of the area. Yeah, it's sort of weird because we are always told negative areas always have to be negative, positive. But I think it's a small price to pay, because if we force areas always to be positive, then we go into all kinds of, well, we want this to be positive, but then we can't, for example, say, the computation becomes more complicated. Anyway, so what did I want to go at? Let's say, for example, we can also combine this, the first unit vector times the other unit vector, and now these are square brackets and these are round brackets. Oh geez. Yeah, it's quite natural to want this to be 0 because it's, well, this rectangle or this parallelogram. Okay, so the idea to decompose something along components is to first ask, what should the formula be, or what is it for simple cases, for unit vectors or vectors along the coordinate lines and vectors that are perpendicular. And then say, well, what happens if we combine simple vectors into more complicated ones? So say, for example, we have a vector v1, v2 that we combine with 0, 1. Yeah. And well, graphically, let's say this is v, and then we combine it with this vector. We sort of already see, well, we want this area. Oh, sorry, no. This is the vector. We want it to be this area here. So and this is a parallelogram, and its base is 1, and its height is just the first component of V. Right? And then you notice that V2 is actually completely irrelevant here. Because all that mattered was this part here. And this part didn't matter at all. So you're sort of led to understand that, yes, we can just decompose this thing. We can just say V1, 0 with E2, and then 0 V2 together with this thing. And this, we've already explained, should just be V1. That's this part here. And this one here, these are two parallel vectors, so it should be 0. So in general, we just want a distributive law. We want a distributive law. We want to be able, or hope that we can find a reason to say, well, whenever we have a sum of two vectors, then it just splits. So it means, let's say we have a vector here, and you know what? Let me just make a horizontal and a vertical vector, because this is what we quite naturally want to split along the horizontal and vertical direction. Yeah. So this is U, and this is V, and then W is somewhere, and then we sort of want to ask whether this area here is the same as U together with W. So that's this area here. Maybe like this. And then V together with W, which actually, if you think about it, is the area up there. All right? So in blue, that's this part here. And now in red, I have colored in this one, and in green, this one. And if you look at this picture for a while, you might notice that yes, it works. Yeah, this is a good principle. Yes, it works. So this little triangle here is the same as this little one there, or you could argue with Cavalieri. Yeah. So this is yes because of Cavalieri's principle. I like to call it the coaster principle. Because if you think of coasters, like beer coasters, when you have a stack of them, you can just shift them horizontally, the volume stays the same. So we have distributive law for this thing, and now we can decompose along the axes. So we can say, and again, if you teach this with students, it's nice to just do a lot of numerical examples first, and then write down the general principle at the very last. Yeah, but this thing, well, what is it? It's V1, V2 together with W1, W2. And so what it essentially is, we need to combine this one and then this one. And then there are two more possibilities. right? So this one, these two are parallel, so this is 0. This one we already saw, this is just two perpendicular vectors, v1, w2. This one is, well, with a sign convention it's negative, and this last one is also 0. So we recover the component formula from before. Okay? So maybe you can split your students into two groups, and one do the area decomposition and the other one does this. Although I would say maybe this is a bit more advanced. Maybe you can have them do the area one first and then guide them through this. I haven't really thought this out yet. But this is actually a really general principle that you can apply to anything with vectors. Just decompose along the components. This is a general principle that I want to take into the third dimension. But before we go into 3D, two last things. First of all, I never really gave this thing a name. I didn't want to call it cross product, but there's an actually cool name for this. It's also called the box product. So it lives in 2 dimensions. It's a product of 2 vectors. The result is a number. It's very closely related to the cross product, but it's not quite the cross product yet. But what it does, it gives the area of the parallelogram that the 2 vectors span. So it's not exactly a box like with right angles, but it's close enough. And the other thing is, I promised that I would tell you where the area is in the cross product, in the dot product, right? So if you think about this thing, u times v as u1 v1 plus u2 v2. Actually, no, sorry. The box product of 2 vectors. Oh, and I used u and v. I want to use v and w. And we've now really found out what this area is. And also as an exercise, you can draw general vectors v and w, and really look for these areas. These are actually 2 rectangles. Maybe I'll just show it to you. So let's say this is v, and this is w. And we said we take v1 times w2, which is this rectangle here. You know what? Let me color the parallelogram in blue again, and then the 2 other things in red and green as before. So it's this rectangle here, this one, and v2w1 is, maybe you found it already, it's this rectangle here. Be careful, it's something that we subtract. And it actually kind of makes sense. Geez, I need to redraw this. Because at first we said only this part. Now we decomposed v into its 2 components, and then we decomposed w into its 2 components. Right? Then we just say, what is the area of everyone with everything else? Okay, and so if we decompose it along V, we did this, yeah. So we said this blue parallelogram is actually this red parallelogram minus the green one. Yeah, and you can check that this is again Cavalieri's principle, right? And this is already a simplification, because at first it was a parallelogram where that it was completely skewed in all directions. Now at least we have two parallelograms where the one is aligned horizontally and the other one is aligned vertically. And then we can actually compute these areas. Because what we actually do, if we want to compute this red parallelogram, it's just we take this rectangle, right? And if we want to compute this green parallelogram's area, all we do is just base times height, which amounts to this rectangle. So there's another interpretation of these things as areas. Now, but there's something else going on with this formula. I can actually write this as a dot product. I just have to be careful. This is V1. Hang on. Now I want to have a dot product with W in front. There's negative V2 and here is V1. Right? It's a dot product. So now we have a way of interpreting the dot product as an area. What is going on? Well, here was my V and somewhere was my W. And what we actually did is compute the dot product of a V with of W with a turned V. Right? So the dot product of these two vectors is nothing but this area. So dotting these two vectors amounts to calculating this area. And you can think about it, well, if the two vectors are perpendicular, then turning V, well, this one by 90 degrees aligns it with W, so there's no area. Right? So maybe I can write it another way. So this is hang on, yeah. Maybe we can write it like this, right? So it's the area spanned by V and a normal to W, right? So there are any two vectors somewhere, living somewhere, and then we say, well, how much are they aligned? Because this also is a way of asking what the dot product is, yeah? Right? If they're completely aligned, the dot product is maximal. If they're at right angles, the dot product is 0. If they're completely opposite, then the dot product is maximally negative. Right? If we ask how much are they aligned, just I say, well, which one? This is V, this is W. We just turn W by 90 degrees and compute this area. Right? Because if they are perfectly aligned, then we get a maximum area, we get a rectangle. So this all is set up for something really nice that happens in 3D. So I'm just going to leave it there for now. And so in 3D, all these ideas about this box product, I want to take you to the third dimension. So in 2D, we had two vectors, and we asked what is the area spanned by the two things. The natural extension is what is the, and now it's not the area between two vectors. We're not quite there yet. It's actually what is the volume spanned by three vectors. Do I prefer mathematics or physics? Do I have to pick? I sort of play jump rope with the two topics, with two subjects. I teach both, and it's I wish I could prefer physics, but physics is in a bad state right now. I mean, fundamental physics. And there's actually quite a big renewal going on in mathematics with the univalent foundations, which I'm a big fan of. So yeah, right now I prefer mathematics, although my degree is in physics. Okay, so in 3D, the question is sort of, let's say we have three vectors, u, v, and w. And now we ask sort of what is this volume? This is what the natural extension is. Yeah. And you might recognize it as the so-called triple product, and it's very strongly related to the cross product. Yeah. But let's keep calling it the box product or triple product, doesn't matter. And this is the notation, because this is the usual notation for the triple product with these angle brackets. And now we had these two approaches that we had in 2D. One approach was to decompose into areas, and there's actually a theorem, a mathematical theorem, that these decomposition proofs don't work in 3 dimensions or higher. Yeah? So our hope is to find a formula by decomposition, by decomposing volumes. It doesn't work. There's actually a famous, it's called Dehn's theorem. It's quite recent actually, that you can't do these decompositions, or you can, but you can't, you don't get very far. You can't, for example, show the area of a pyramid or of any polyhedron in terms of decompositions into cubes or something. So the other path is to decompose along components or along the axes. That is, we first ask, what should the formula that we're hoping to get give us for the unit vectors, and then check whether when we combine vectors into sums of vectors that this volume doesn't change, right? So the first step is what should this thing be for unit vectors? And the other is, does, do the volumes add properly? Yeah. So that is when we say, for example, we have two vectors that you combine in the first argument, that we can actually split this up. Like this. Yeah? Because then we can take any vector and just take any box product and just completely decompose into all the components, and then we're just left with box products of unit vectors. Yeah? This is the strategy for getting a formula. So, and I'm actually getting a bit faster now. So it's quite understandable that we want this box product to be 1 because it's just the unit cube. Yeah, but then also we want, say, E2, E1, E3 to be -1. It might, again, so we go into oriented volumes, and there's a way to justify this, again, by saying, for example, well, I want E1 negative E2, E3 to be -1, and then this cube would be, where is it? It's sort of, if this is X and this is Y and this is Z, it's this times this times this, sort of this cube. And then we, oh, you have to rotate it in some way. Never mind. And then we also want, for example, E1, E1, E3 to be 0. There are a number of other combinations, but this is how we want oriented volume to work. And again, we want volume to have a sign also, because why do we want volume to have a sign? I'm not entirely sure how I would justify that in front of a novice. Yeah. And now the other question is, for example, this thing the same as this? And I really should have, I don't know, prepared this better. Maybe I have some nicer visuals, but okay. So we have two vectors that we sort of concatenate, and then we have a V somewhere and a W somewhere. And the question is whether this volume, again, let's make it blue, is the same as it's the 3D variant of what I drew before. But for some reason I can't visualize it properly right now. It's this one, and then the green one would be, I hope you understand the idea what I meant, but it's hard to draw, and I should have really prepared this with some nice GeoGebra. But again, it turns out that this can be justified just geometrically. This again is Cavalier's principle. Yeah. So any parallelepiped and because this is the kind of volume of that 3 vector span, it can be broken down via this distributive law into just combinations of unit vectors. Yeah? Can be broken up into combinations of these things. And these are just, cubes, right? So, so at this point it's starting to get a bit tedious. So what we do is u1, u2, u3, we write general coordinates. And again, you can do some introductory examples. And then that's actually one that I wanted to do, but I'm actually gonna skip it. And then say, well, this is u1, e1, u2, e2, u3, e3. And then the second component is v1, e1, and so forth. And then you split it up and say, well, it's also sort of a threefold distributive law. You get u1, v1, w1 times, well, the first unit vector, box product with its box multiplied with itself 3 times. And then you get u1, v1, w2 of e1, e1, e2. And at this point, you might already recognize that a lot of these combinations are just 0. The first non-zero one will be u1, v2, w3, which is multiplied with just the unit cube, which is 1. And then there will be things like u1, v3, w2, and then you already see that these vectors are flipped, so they give -1. And when the dust has settled, you get a formula which is quite the monster. But it's, I really say, I have done this with the students. There's a payoff here. If anything, it's a nice algebra training, but you get u1, v2, w3, minus this one, and then you get u2, v3, w1, and u2, v1, w3, and then you get u3, v1, w2, and u3, v2, w1. Quite a big formula, and if you want, you can make a little excursion about cycles, about permutations, yeah. Permutations of 1, 2, 3, and the associated signs. And geometrically, this is the decomposition via Cavalier's principle. So you shear the cuboid, the parallelepiped into all kinds of cuboids, and actually just 6 cuboids are left, and 3 of them count positively and 3 of them count negatively. And just because you're just shearing things along coordinate axes, you can just it's just Cavalier's principle, so the volume is conserved. Yeah, and actually you can take this into higher dimensions even, and what this amounts to is developing a determinant along a line or column. So if you've learned this in college, how to compute the determinant of a big matrix, and the determinant is sort of the n-dimensional volume of the column vectors of the parallelepiped that they span. What you actually do when you develop along a line or column is that you shear this parallelepiped along coordinate axes into lower dimensional, well, or more aligned variants of these parallelepipeds. And then if you take this down to the first, until you've completely untwirled the whole determinant, that amounts to decomposing this parallelepiped into all kinds of cuboids with a sign. So there's a n-dimensional Cavalieri's principle going on behind the formula for the determinant. But here, as a little exercise, you can compute this product here. So, and also look at it, what this is geometrically, right? But you can do this on your own. But there's something interesting going on with this formula. I see shadows of the two-dimensional box product in here. And it's a bit more, what you actually do is we have U1, U2, U3 dotted with V2, W3, V3, W2, V3, W1, and V1, W2, and V1, W2 minus V2, W1, and there's your cross product. This is where this is coming from. It's actually from computing a volume. Yeah. This is where this formula comes from. And now we can go back to the geometry and say, well, we are dotting something. Actually, let me draw this again. Hang on. So I wanted to, never mind. So let's have this be U now, and this is V and this is W. So this cuboid, no, that's parallelepiped, this whole volume is a dot product of this vector with a new vector. And now if you think about it, hang on, I have to collect my thoughts. Okay, 10 more minutes. Yeah, no. What? Vector areas. I want to connect it to the other formula for the cross product. Right? So this volume is actually, hang on. I wanted to show why this thing now is perpendicular to V and W. But first, the difficulty here is that these are areas anyway. Yeah. So what sense would it make to draw this vector in here, right? It's not a length. Yeah? It's area. So but something that might be interesting here is to just compare this formula with another way of computing this area. Another way of computing the area, the volume is to say, well, it's base times height. Yeah? So we take this base, and then the height, actually we have to sort of project U down here, like this. And it's, how does that work? Man, I had it. Because I really wanted to show why is this, first of all, why is the length of this whole thing, right? So when we square these and add them and then take the square root, why would this have anything to do with area, let alone this precise area? And the idea is, okay, the idea is, oh, yes, of course, yeah. So first of all, this is a vector of areas. So it's not a vector that has a length, but it's more like a vector that, as we use it in physics. Yeah? So it's a general vector. So it doesn't have a length, but it has a magnitude. Right? So in physics, we have all kinds of vectors, but we don't measure that in meters. We draw the arrows on paper to show where they go and how long they are, but the length is essentially arbitrary. Yeah? We have to pick a scale and say, okay, that much represents, say, 10 newtons of force, and then we go on and draw our force diagrams. But the length is not a physical length. So it's the same thing going on here. So this represents an area in size and direction. So the components are areas. It's not quite obvious why we should be able to apply Pythagoras and then the whole length of this, the same way we do it for displacement vectors, should give an area. But at least it has a direction. Yeah. So size aside, what is the direction of this vector? And oh yes, okay, now I have it. This is the thing. If u is perpendicular to v and w, so actually we don't use the general case, we really say, here's my v, here's my w, and now I pick a u that is already at right angle, so there's no need to project. Right? So there's a right angle here and a right angle here. Yeah. Then we know that the whole volume is just u times this area down here, this parallelogram. But we know that it's also just, well, a dot product between the u and some special area vector, right? But the only way that these two vectors dot together are just their lengths together is if A is parallel to u, so A as a vector is perpendicular to v and w. Or you can also check that v cross w, times v is 0, and also times w is 0. Right? And now, I think we have it. Well, no, not quite. Actually, sort of, we do have it. So, the so-called length of v cross w is the area or spanned by v and w. Yeah. So even if they are in 3 dimensions, by going through the volume, you can really see that, yep, this area in its orientation, but also in its size, is represented by this thing. And now is the last thing, which is these components. Let me write this up again. V cross W is V2, W3, V3, W2, V3, W1, V1, W3, V1, W2, V2, W1. These components, each one itself is an area. Where is that area? Because if you look, each component itself is a replica of the box product from 2 dimensions. And where it is actually, now I have to draw really well. Let's say here is V and here is W. Oh, I'm already messing up. So this area gets projected. So for example, this formula down here is the area spanned by the projections of V and W onto the XY plane. Right? And this one here is the projection onto the XZ plane. So I don't know where that is, but it's somehow here. Project not along that plane. And then the third one is somewhere back here. And I need a third color. That's this one. And let's give these names. Let's call this A. And this is A1. No. This is A1. This is A2. This is A3. So now we have established that A1 squared plus A2 squared plus A3 squared is A squared. You might say, wow, this is okay, squaring areas. But if you think about it, this is a natural extension of what is already going on just for simple displacement vectors. For displacement vector in 3 dimensions, what do? We project, let's call this one, I don't know, V, right? We say V1 squared plus V2 squared plus V3 squared is the whole length squared. Why? Because we just project on the x direction, on the y plane, on the z plane. And we know that this squared is this squared plus this squared plus this squared. I messed up the order of the colors, but this is what's going on, right? Here we have a simple displacement vector, and we project it onto the axes, and the 3 components along the axes squared give the whole length squared. So this is our 3-dimensional Pythagorean theorem. But actually, here's another version of another 3-dimensional version of the Pythagorean theorem. We have an area vector, or just a parallelogram somewhere, and I think it might even work for any area. Not too sure. And then we project this area onto the planes, not onto the axes, but onto the planes, and we also get 3 shadows, and the sum of the squares of the shadow areas is the square of the original area. And now the last thing, little exercise for you at home, is show this variant or version of 3-dimensional version of the Pythagorean theorem. You have a tetrahedron with a solid right angle in the middle, so it's in the back. Yeah, and of course you have areas A1, A2, A3, and then you have this sort of 4th part here on the front. So it's a bit more complicated because these are triangles, not parallelograms, but it's in there. Yeah. Show that for this sort of 3-dimensional right-angled tetrahedron, the sum of the squares of the legs is the square of the hypotenuse, all these being surfaces. Yeah. Okay. That is everything I wanted to show you. Lots of hiccups were happening today, and yeah, I wanted to be better prepared, especially with the visuals. Hopefully, I think I'm planning on making this a regular thing because I have lots of ideas about other parts of school mathematics that I say, here's a new, fresh approach of doing this. And yeah, let's see how much I can do next to my teaching, but my plan would be to make this weekly, so at least as long as Saturdays are not going out days for the foreseeable future. Yeah, I think we have it. That's almost everything. So I don't really want to get into these questions that you've asked about, especially IQ. It's a topic for another day, and it's yeah, a lot of people have lots of misconceptions about this and what IQ is or should be, or I don't engage. I do what is fun, what I find is fun. I show it to people, and some of them like it, some of them don't, and it's yeah. Anyway, that was everything for today, and maybe you've had some new ideas for your own teaching or for your own understanding of vector geometry. Here we go. And yeah, so next Saturday, I was thinking about doing something about, what was it? Oh yes, limits. Yeah. So I hope I see you see you next time about this. And yeah, over and out.